Okay, so we're constantly getting hit with health news, right? But have you ever really stopped to think about where it all comes from? It turns out understanding how this research gets made isn't just for scientists in a lab. It's a critical skill for, well, all of us. So today we're going to pull back that curtain and see how we actually know what we know.
You've seen this a million times, I'm sure. One day, coffee's your worst enemy. The next day, it's a superfood. It's confusing. And that confusion is exactly why we need to look under the hood at the science itself. Because it's really not about the crazy headline. It's about the quality of the journey that got them there.
And that's exactly what we're going to do. We're going to follow that journey. Every single piece of health information we rely on started out as just an uncertainty, a moment where some researcher decided, I need to find an answer to this. So let's start at the very beginning. Long before anyone collects any data or makes any big announcements, a researcher has to come up with the perfect question. This is the foundation, the absolute bedrock for everything else that's about to happen. At its heart, a research question is actually pretty simple. It's a specific I don't know that somebody wants to figure out. But this isn't just random curiosity. No, it's a super focused question that's designed to be answered with actual, concrete measurements from a particular group of people. Now, these questions really come in two main flavors. You've got your descriptive questions, which are all about just measuring something. They ask how many or how much of a problem is out there. Then you have analytical questions. These are the ones that ask why, and they try to get at an answer by comparing different groups. To answer those how many questions, researchers have two main tools. And honestly, the best way to think about them is to picture the difference between taking a single photograph versus filming an entire movie. First up, we have prevalence. This is the snapshot. Imagine you just freeze frame a moment in time. Prevalence tells us how many people, all the old cases plus all the new ones, have a disease right at that specific moment. It gives you a really clear picture of the total burden of a condition on a community right now. Then there's incidence. And this is the movie. Incidence tracks the story as it unfolds over time, and it only counts the new cases that pop up. This is all about risk. It tells you how fast something is spreading and what the odds are of getting it. Let's think about it this way. A chronic disease like diabetes, it's like a bathtub where the tap is just dripping in slowly. That's the low incidence of new cases. But the drain is plugged, so the water level keeps rising over time. That's the high prevalence. The common cold, on the other hand, is like a sink where the faucet is blasting full on. That's a high incidence. But the drain is wide open, so the water goes out as fast as it comes in. The prevalence, the amount of water in the sink at any one time, stays low. And this all leads to this just brilliantly simple little formula that ties it all together. P equals I times D. The prevalence of a disease is just its incidence, the number of new cases, multiplied by its duration. This little equation, it's the key to understanding that whole dynamic between new cases and the existing number of cases for any health problem. So once we know how to measure a problem, the next logical step is to describe it. And this is where descriptive studies come into play. They're not designed to prove anything, but they are absolutely essential for gathering those first critical clues. A really common starting point is something called a case series. This is when a doctor notices, hey, a few of my patients have the same really weird condition, and they write about it. Now, there's no comparison group, so you can't prove what caused it. But what you can do is sound an alarm and get a good hypothesis going. And the power of a simple case series can be absolutely world-changing. Back in 1981, a report on just 5 men with a rare type of pneumonia was the very first signal flare that a new, terrifying disease, what we would later call AIDS, had just emerged. It all started with just paying attention. Those first clues from descriptive studies are vital. But to really put a hypothesis to the test, researchers need something more powerful. And that brings us to the main event, analytical studies. The two absolute workhorses of this field are the cohort study and the case control study. Think of it like two totally different ways to solve a mystery. A cohort study looks forward in time. It starts with people who are exposed to something and then waits to see who gets sick. A case control study does the opposite. It works backward. It starts with people who are already sick and then looks into their past to try and find the cause. So here's how a cohort study works. You find a big group of people, your cohort, and you separate them into those who have an exposure and those who don't. Then, you just follow them. You follow everyone, sometimes for decades, and you simply compare who ends up developing the disease in each group.
And the most famous example of this has to be the Framingham Heart Study. Since 1948, it has followed thousands of residents of one town in Massachusetts. It's because of this incredible study that we know about the links between things like high blood pressure, cholesterol, and heart disease.
But what if you don't have decades to wait around? Well, that's when you use the opposite approach. You work backward. In the 1950s, two researchers, Dahl and Hill, were desperate to find out why lung cancer rates were skyrocketing. So they found patients who already had lung cancer, those are the cases, and they compared their past smoking habits to similar hospital patients who didn't have it, those are the controls. The difference was staggering, and it gave us the first rock-solid proof that smoking causes lung cancer. But this backward-looking method has one big potential pitfall, something called recall bias. Think about it. Someone who's sick is probably going to think a lot harder about what they did in their past than someone who's healthy, and that difference in memory can sometimes twist the results.
So when do you use which one? Well, here is a fantastic, simple rule of thumb. If you're studying a rare exposure, like maybe an industrial chemical spill, a cohort study is your best bet. You can find the people who are exposed and follow them. But if you're studying a rare disease, a case control study is way more efficient. You just find the few people who have it, and then you look backward.
Look, no study is ever perfect, not a single one. Good researchers know this, and they're always on guard for different errors and biases that can send them down the wrong path. It's all about knowing the rules of the game.
And these errors come in two basic types. First, there's random error. That's just the natural static or variation that happens by chance. The best way to deal with that is just to get a bigger sample size. But then you have bias, or systematic error. This isn't just chance. It's a fundamental flaw in how the study was designed. And making the study bigger won't fix it. Only a better design can.
One of the biggest, trickiest sources of bias is something called a confounder. This is the hidden variable. It's a third factor that's tangled up with both the thing you're studying and the outcome you're measuring. For instance, early studies found a link between drinking coffee and heart disease, but it turned out that coffee drinkers were also way more likely to be smokers, and smoking was the real cause. In that case, smoking was the confounder.
Whew, okay, so after that quick trip through the world of health research, let's just step back and bring it all home. What are the key things you should take away from all this?
Okay, let's pack your new mental toolkit. First, remember, every single study starts with a question. Second, know the difference. Prevalence is that snapshot in time, while incidence is the movie playing out. Third, cohort studies march forward, from cause to effect. Case control studies look backward, from effect to cause. And finally, and this might be the most important one, always remember that the study's design is what really determines how strong the evidence is. So now you've got the tools. The next time you see some wild headline about coffee or anything else, you can look right past the hype. And instead of just swallowing the conclusion, you can ask a much, much better question. What kind of journey did they actually take to get that answer? Thanks for listening.